This section on Fresnel equations is the way in which we calculate how much of the light gets reflected at any particular surface, going from, for example, going from air into glass, how much gets reflected at the surface and how much gets transmitted at the surface. If we think about the ray coming in, the incident ray coming in and hitting the surface, then some of the light will be reflected and some of the light will be transmitted. And Fresnel equations tell you, well, how much of the light will be reflected and how much of the light will be transmitted. It depends on the angle of incidence and the angle of transmission. So it depends on the refractive index in the incident material and the refractive index in the transmitting material. But it also depends on the polarization of the light. So if we imagine on the plane of this page that the electric field is oscillating in the plane of the page, then we can represent that by a vector which is parallel to the plane of the page. And if it was coming directly out, perpendicularly out from the page, then we could draw that as just a little dot to say that it's coming out of the page, and that would be our perpendicular polarization. The amount of light which gets reflected and the amount of light which gets transmitted depends on this polarization. It depends on whether the light is polarized parallel or perpendicular. It depends on the refractive indices, and it depends on the angle of incidence. And so Fresnel's equations just pulls all those together so that we can calculate just exactly how much of the light does get reflected and how much is transmitted. So we'll consider a plane wave, a nice simple plane wave oscillating in the plane or out of the plane or at some angle to the plane of incidence. And we have our equations for the electric field of the incident reflected and the transmitted rays. Again, for insulators, we're going to assume that the magnetic properties are negligible and we don't have to worry about them. And so what we want to know is what fraction of the light gets reflected, what fraction of the light gets transmitted. So that's these equations. Fresnel equations will tell you that. And you can see that we have the amount of light which is reflected if the polarization is parallel to the plane of incidence, the amount of light which is transmitted if the light is parallel to the plane of incidence, the amount of light which is reflected if it's perpendicular, and the amount of light which is transmitted if it's perpendicular to the plane of incidence. And we define these reflection coefficients and transmission coefficients as the amplitude of the reflected ray compared to the amplitude of the incident ray, or the amplitude of the transmitted ray, wave compared to the amplitude of the incident wave. So going back here, let's just clear all that. Then again, if we have our surface, the wave coming in, the wave, some of it being reflected and some of it being transmitted. Then if we have our amplitude for our input wave here as EI, and this is the amplitude of the reflected wave, ER, and the transmitted wave, taking the magnitude of them, then our value for the reflectance coefficient is, the reflection coefficient is the magnitude of ER over the magnitude of the incident. And again, the transmission is the ratio of the amplitude for the transmitted wave compared to the amplitude of the incident wave. And we've said that it depends on the polarization, so it depends on whether the vector is in the plane, as in here, or whether it's pointing directly out of the plane. Now, if so that we'll have our parallel and our perpendicular polarizations. Now, if you imagine looking down this ray, if we have our eye at that point, and we're looking along the path of the ray, then we will have our parallel plane and our perpendicular plane. And so if the light just oscillates up and down in the parallel plane, then we can use our expression for R parallel. If it goes backwards and forwards in the perpendicular direction, then we can change that to R perpendicular. If it's going at some angle to the plane, then we can break it down just as we can with any other vector. We can break it down into a perpendicular component. So if that's E incident, then we can break that down into an E incident perpendicular and an E incident parallel. Okay. So these equations look pretty horrible. Don't worry about memorizing them. If you need these equations in the exam, I will give you them to you on a data sheet. So you don't need to memorize these equations. But just bear in mind that you have a polarization dependence for these reflection coefficients. Now we can plot those curves, and what we'll see is going from a low refractive index into a high refractive index. So when Ni is less than Nt, then we get a set of curves that look like this. So you can see the transmission starts off at some value there. That's about maybe 0.8 or something. And that depends on the difference in refractive indexes. It depends on the value of Ni and the value of Nt. And as we increase the angle of incidence, as we go to 90 degrees of angular incidence, we'll see that none of the light is transmitted and all of the light gets reflected. So if we imagine the angle of incidence increasing until eventually at 90 degrees we're travelling along the surface, and obviously if we're travelling along the surface then none of the light gets through. For the amount of light which is reflected, then again if we go towards 90 degrees then all of the light will be reflected. If it's not transmitted it must be reflected. The energy has to be conserved, and so if you put 1 unit of energy in, you must get 1 unit of energy out, and if 0 units of energy are in the transmitted beam, then all of the energy must be in the reflected beam. So we get a coefficient of -1. Now the -1 tells us not just about the magnitude but also the direction. So if the input polarization is pointing in that direction, then for the reflected wave it will be pointing in the opposite direction. Okay, so the -1 here tells you that the vector has changed its orientation. The perpendicular reflectivity, we have, it starts off something about maybe 0.2 and then goes up to 1. Much more interesting though is for the parallel component, and it starts off at maybe plus 0.2, it goes through 0 and then ends up at 1. And this 0 point is called the polarization angle, confusingly. But we've also already seen this, and we called it the Brewster's angle. So the amount of light which is reflected, if it's polarized parallel to the plane of incidence, will be 0. And all of the reflected light at this angle will be polarized perpendicular to the plane of incidence. This graph shows if we go from a case where Ni is bigger than Nt, and again, just looking at the reflections coefficients, you'll see again for the parallel component we go through Brewster's angle, and for both of the parallel and the perpendicular components, we get to the point where we have the critical angle, total internal reflection, and so all the light gets reflected, and the reflection coefficient is 1. So 100% of the light gets reflected, none of the light gets transmitted. Okay, so you'll see in some textbooks it might be referred to as the polarization angle, but I'm only telling you that in case you see it. I tend not to use that notation, use Brewster's angle and critical angle. So this, let me just see if I can. So these diagrams show you what happens as this angle of incidence increases. You see that our input vector is pointing in that direction out of the plane, so it has a perpendicular component and a when it gets reflected, you'll see that it again has a perpendicular component and a parallel component, and the perpendicular component has a negative sign. So in the curve above it was maybe minus 0.2. So that means that the vector will now point through the other side of that plane, this grey plane that we've drawn here. If we get to Brewster's angle, then again what we have is we have an input vector which is pointing some way at an angle out of the plane, and for the reflected beam we have no parallel light being reflected and we only have perpendicular light being reflected. And if we go beyond Brewster's angle, then again what we have, input vector pointing out of the plane, and this time both the coefficient for the parallel and the perpendicular component are negative, and so the vector, the resulting vector, flips through both axes. We can do the same thing again going from high refractive index to low refractive index, and you'll see the same sort of thing. The different values of R, if R is positive or negative, depends on whether it flips or not, and the same here for less than Brewster's angle and for some value between the critical angle and Brewster's angle.